Alright, welcome. Today we're looking at the real number system. Alright, and to be specific, we're going to be looking at binary operations. Before we can look at binary operations, I'm just going to show you the CAPE syllabus. So the CAPE syllabus, we're required to know about the real number system, and we are required to know about binary operation. And so before we can get into binary operation, we have to get into the real number system. So the real number system, this falls under module 1 of unit 1. So this is module 1 that we're going to be looking at. So I'm just going to show you right here. This is the CAPE syllabus, the real number system. And under the real number system, you're going to have to learn to be able to perform binary operations and use concepts of identity, closure, inverse, commutativity, associativity, distributive addition, multiplication, and other simple binary operations. So that's what we're looking at right now. We're looking at the real number system. And under the real number system, we're going to look mainly at binary operations. Alright, but before we can look at binary operations, as I've been saying, we have to look at the real number system. So the question we'll ask ourselves is, what is the real number system? The real number system, before we can look at the real number system, we have to break down the real number system some more. And so under the set of real number system, we have to first go back to what we were introduced to in basic school. Remember when you were counting? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, go on. I will say that this is known as the set of counting numbers, or right now what we call it is natural numbers, and that's denoted by n. So that's the first thing. We have natural numbers, which are the set of counting numbers. Then we go on to whole numbers. We'll learn about natural numbers plus the inclusion of the number 0, we call that whole numbers. And so whole numbers are natural numbers plus the inclusion of the number 0. And that then gives you the set of whole numbers. Now, as we leave basic school and we start with primary school, we start hear about positive and negative. Right? Them start teach about directed numbers, that kind of like grade 3, grade 4. And so then positive and negative whole numbers now are then being defined as integers. So negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. All of these are being defined as integers. Alright? And so far what we can clearly see is that natural numbers is a subset of whole numbers. Whole numbers is a subset of integers. And so therefore whole numbers is also a subset of integers. The next thing is that we have what is known as the set of rational numbers. And so the set of rational numbers, these are numbers that can be expressed as a positive or negative fraction. So once you think of a number that is a fraction, it's a rational number. So let's say, for example, rational number is denoted by the letter Q. So for example, right here we have negative 4 over 5, negative 3 over 7, 8 over 9, 25 over 3. These are all rational numbers. Alright, these are all rational numbers. So these are all what? Rational numbers. Alright, as long as it can be expressed as a fraction. So even the number 5 is a rational number because 5 can be expressed as 5 over 1. And so 5 is a rational number. So 5 is also an element of Q. And so if 5 is a rational number, then what we can therefore conclude is that integers is a subset of rational numbers. We can conclude integers is a subset of rational numbers. Now look at this question. It says a rational number can also be written as a decimal, which is either terminating or recurring. What does terminating mean? Terminating means that when you write it as a decimal, it stops. It's not continuing. So for example, the number 0.2. This is a rational number. It's terminating. This is really just 1 over 5. right? That's that. 0.2 is 1 over 5. So if we were to, we learned how to convert from decimal to fraction. So learning how to convert decimal to fraction, we would have been able, to show that this is 1 over 5, right? This is primary school math. I'm not supposed to be getting into that. All right, now recurring is something like 0.333333. So it continue and continue. So you put a dot over the last three to show that it continue. This is recurring forever. And so this, we know 0.333 is 1 over 3. Right? So 1 over 3 is a recurring decimal, but it's still a rational number because why? It can be expressed as a fraction, n over d. As long as it can be expressed as a fraction, it is a rational number. So now, the next thing that we're going to be looking at, this question, it says show that negative 0.555 can be expressed as a recurring decimal. Show that, that part of the question is missing. Show that these can be expressed as rational numbers. Alright, so this question right here is to show that these can be expressed as rational numbers. When you do that, you're going to get that this one should be negative 5 over 9. That's what the first one should work out to be. 1.5656, where there should be a dot over 5 and 6. Alright, so those should work out to be a fraction as well, and 4.357. Just some practice, just to get warm up, right? These are primary school questions, how to convert decimals to fractions. We won't get into that. Alright? Now the next thing after decimal, after fractions, is irrational numbers. What are irrational numbers? Irrational numbers, these are numbers now that we cannot find the exact value of them as a fraction. So for example, growing up, we always learn that pi is 22 over 7. That's an estimated value of pi. Sometimes you hear that pi is 3.142. Another time you hear that pi is 3.1415, and so there's no exact value of pi, and so we use approximated value of pi. And this approximated value of pi, well, we cannot find the real value of pi, and the real value of pi is an irrational number. It's an irrational number because it really cannot be written as a decimal. It doesn't terminate, all right, and it's not recurring either. It's just continuing and continuing and continuing. So here are some examples. The square root of 3. So all numbers that can be left in exact form as a third are irrational numbers. Constants such as e and pi, those are irrational numbers. So here pi is 3.14159 and it continues. Irrational number. All right. So now finally we can get to the set of real number. Now the set of real numbers constitute of all rational and irrational numbers. And we know that all rational numbers includes integers, whole numbers, natural numbers. Alright? And so all of this set combines together give us the real number system. Easy, soft, right? That's the beauty of mathematics. So the real number system, first the real number system that we learn about is a set of natural numbers. These are all counting numbers. Then after the set of natural numbers, we have whole numbers. And whole numbers are all natural numbers including 0. After whole numbers now, we have integers. So we have integers, which includes positive and negative whole numbers. So integers just going to include now the -1, the -2, and stuff like that, plus all the whole numbers. After integers now, as we said, we have the set of rational numbers. Right? We have the set of rational numbers. And oftentimes rational numbers is represented by Q. Q. So we use Q to represent rational numbers. Alright? And then what they use to represent irrational numbers is Q prime. And so if this is the whole set now, then what we have now is that the universal set is a set of R, which is real numbers. And then the complements of all of these sets is known as Q prime, which is irrational numbers. Q prime, or it's denoted as I, irrational numbers. These are numbers like pi, square root of 2, etc. Alright, and so this is what we have now, and this is denoted as the real number system. So now that we've been introduced to the real number system, the most important thing that we need to know about the real number system is operations on the real number system. Because we use the real number system, we have to look at the operations under the real number system. So we have to look at addition on the real number system, subtraction, division, and multiplication. Beautiful. Alright? Beautiful. So we're just looking at now the operations of the real number system. So let's go about doing that. Alright, so before we can look at the operations of the real number system, we have to first look at the axioms of the real number system. What are the axioms of the real number system? So the axioms of the real number system, first and foremost, we need to talk about numbers that we know are in the real number system. We know about even numbers, we know about odd numbers, we know about adding two even numbers, adding two odd numbers, finding the difference between two even numbers, the product of two even numbers. All of that, all of these operations that we're doing are axioms of real number because they fall under the real number system. So let's look at what happens under the real number system. So under the real number system, let's start from the even numbers. So we have an even number, right? Even numbers are numbers like, what are even numbers? Even numbers are numbers like 2, 4, 6, 8, right? 2, 4, 6, 8, negative 2, 0. These are all even numbers. And so any even number can be expressed as 2k, right? Any even number can be expressed as 2k. And why is that? Because let's say k is equal to 1. So let k be equal to 1. If k is equal to 1, you get 2 times 1 is going to give you the number 2. And 2 is an even number. So any number, if you choose any value for k, let's say you choose the k equal to 2. If you choose k equal to 2, then what you get, sorry I didn't erase, 2 times 2 is 4. If you choose k equals 0, you get 2 times 0 is 0. Alright, if you choose k equal 99, you get 2 times 99 is 198. And 198 is still an even number. And so any number that is expressed in the form 2k, where k is an element of natural number, then we say that this is a even number. Alright, so that's the first axiom of real number. Any number, any even number may be represented as 2k. Now if we represent an even number as 2k, then we can represent an odd number by 2k minus 1. If we can represent an even number by 2k, then an odd number can be represented by 2k minus 1. Alright? Now, it's either we can represent it by 2k minus 1 or 2k plus 1. That makes sense? Because if 2k is an even number like 98, then 2k minus 1 must give it 97. And 2k plus 1 must give it 99. And so clearly, any even number, and then you subtract 1 from it, or you add 1 to it, you get a odd number. Alright, so that's the second one. Then now adding two even numbers. If we're adding two even numbers, we're adding 2k plus 2h, right? Because 2h is just the variable we use here. right? Where h is also an element of natural number or counting number. And so 2k plus 2h, we can factor out 2 and we get 2 times k plus h. And so this is the form that the sum of two even numbers take. Now let's say we want the difference of two even numbers. It would be 2k minus 2h, right? So let's change the plus to minus for difference. And then 2 times k minus h, and that's the form of two different even numbers. Now let's say we want now the sum of, this should be the sum of two even numbers is even. So the sum of two even numbers is even from right here. So the sum of two even numbers is even. Alright, now this part where it says the sum of two even numbers, right here, sum of two odd numbers, it should be odd right here. The sum of two odd numbers, the sum of two odd numbers is even. As if we're adding an odd number 2k plus 1, or adding 2k, 2, this should be 2h, or adding another odd number 2h plus 1, right? Let's say we add a different odd number 2h plus 1. So when we add them together, we get 2k plus 1 plus 2h plus 1. So that's 2k plus 2h plus 2. And so we can factor out a 2 and we get 2 times k plus h plus 1. And that's the sum of two odd numbers is even. So for example, if I were to add two odd numbers 5 plus 7, 5 plus 7 is equal to 12. And 12 is an even number because it can be written as 2 times 6. Right? So it can be written in the form 2 times k. And so it is an even number. Now the difference of two odd numbers is odd. 2k plus 1 minus 2k plus 1. Then what we're getting is, we're taking the difference of them now. So we get 2k minus 2k. This should be h. Don't know why I put k right there. So this should be 2k minus 2h plus 1. And then the 1 minus the 1 that cancel. And so we get 2 times k minus h. And so the difference of two odd numbers is even. Now the next thing we need to talk about is the product of two even numbers. The product of two even numbers, think about it, when you multiply 6 times 6 you get 36, that is still even. You multiply 4 times 4 you get 16, that is even. So when you multiply any two even numbers, you're always going to get an even number. Guaranteed. And so if you multiply two even number 2k times 2h, you're going to get 2 times 2kh, which is even. Because this 2kh is just really one number. We can call this one number j. And 2 times any number j is even. And so this is how you show that the product of two even numbers is even. Now the product of two odd numbers is odd. So if you multiply two odd number 3 times 7, you get 21. Or you multiply two odd number 5 times 9, you get 45. The product of two odd numbers will always be odd. And so 2k plus 1 times 2h plus 1, you're going to get an odd number. How do we know we're going to get an odd number? Even number is 2k plus 1. And so the result is going to be in the form 2k minus 1 or 2k plus 1. That's the result of an odd number. So look at this. This 2 times 2kh is going to work out to be even. This 2k is even. This 2h is even. And so we'll add 1 to the sum. We're going to get an odd number. Now finally, the last axioms of real numbers is the product of two numbers with opposite signs is negative. The product of two numbers with opposite sign is negative. So for example, if I multiply 5 times negative 1, then the result is going to be negative. Negative means the result is going to be less than 0. 5 times negative 1 is negative 5. If I multiply 3 times some negative number, negative 2, the result is going to be negative 6, which is still less than 0. And so anytime I multiply two numbers of opposite sign, This is a plus 3 and this is a minus 2. The result is going to be negative. The result is going to be negative when I multiply two numbers of opposite sign. This is a key. You must remember this axiom. So here's an example. It says if A is greater than B, so if A is greater than B and K is less than 0, then show that KA is less than KB. Now if A is greater than B, so this is how it works now. So then tell us that A is greater than B. So if A is greater than B, then if we subtract B from both sides, so if we subtract B from both sides, we get A minus B is greater than B minus B, but B minus B is 0. And so we get A minus B is greater than 0. And then the question also tells us that K is less than 0. And so if K is negative and A minus B is positive, whenever we multiply a positive times a negative, so we have a positive and we're going to multiply it by a negative, then the result is going to be positive. It's negative. So K times A minus B is going to be less than 0. K times A minus B is going to be less than 0 based on the axiom of the real number that when you multiply a positive by a negative, you get a negative. And so what this means is that if we multiply then K times A, we're going to get KA minus K times B, we're going to get KB. So KA minus KB is less than 0. And so then the final step, which is right here now, we just bring over the KB, and so we get KA is less than KB. And so those are the axioms of real numbers. So first, remember, we looked at the definition of the real number, which shows that the real number constitutes of the set of the union of the rational and irrational numbers. Now that we look at the axioms of the real numbers, the next thing we need to look at is the operations of real numbers. And the four basic operations we learn from CSEC, from primary school, are addition, subtraction, multiplication, and division. So you see how much things we have to do before we get to binary operation? Alright, so let's look at the real number system. Let's look at addition, subtraction, multiplication, and division. So let's go. So the commutative law. Alright, so that's the first property that we're going to look at, and this one is of course for addition we'll start with. So first and foremost, what is the commutative property? We learned this from primary school. So the commutative law states that if you add two numbers, the order don't matter. So A plus B is the same as B plus A. So if I add two numbers such as 1 plus 3, that's 4. I can say 3 plus 1, that is 4. So that's all the commutative law states. An arithmetic operation is commutative if the order does not change the result. So A plus B is B plus A. Alright, where both A and B are real numbers. Because remember, we're looking under the real number system. Then now multiplication, commutative property is if A times B is equal to B times A. Alright, and the commutative property is always true for addition and multiplication, but is never true for subtraction and division. Let's look at why. As I said, if we were adding 1 plus 5, it's the same as 5 plus 1. And so that is true. Now, if we were timesing now, 1 times 5, it's going to be the same as 5 times 1. That is true. Now, commutative property is never true for division and subtraction. And look at it why. 1 minus 5 is not going to be equal to, it's not going to be equal to 5 minus 1. 1 minus 5 is negative 4, 5 minus 1 is 4. The same way, 1 divided by 5 is not going to be equal to 5 divided by 1. And so what we can clearly state then is that the commutative property, what we can clearly state is that the Commutative property only apply for addition and multiplication of real numbers. As two real numbers, it only apply for addition and multiplication. So now the next thing is associative law. So now that we're looking at the associative law, right? So of course we start with addition. And so the associative law does states that if we're adding three numbers now, the order don't matter. If we're multiplying three numbers, the order don't matter. But associative law is never true for subtraction and division. So let's look at why. So we have three numbers, a plus b plus c. We can add a and b first and then add c. Or we can add b and c first, then add a, but the order don't matter. Likewise, for multiplication, we can multiply a times b first, right? And then multiply c, or we can multiply b times c first, and then multiply a. The order does not matter. So let's look at an example. So for example, let's say we multiply 1 times, let b be 2 and c be 3. 1 times 2 times 3. 1 times 2 times 3, I bracket the 1 times 2. 1 times 2 is what? 2. And so I get 2 times 3. And 2 times 3 is indeed 6. Now look at if I had said 1 times 2 times 3. And let's say I had start by multiplying 2 times 3 first. So 1 times 2 times 3, where 2 times 3 is 6. And so I get 1 times 6. And then 1 times 6 is 6. And so clearly, it holds true for multiplication. Now we don't need for add. Look at it. 1 plus 2 is 3. 3 plus 3 is 6. If it was addition right here again, 2 plus 3 is 5. 1 plus 5 is 6. And so it holds true for addition as well. Now here is where it don't hold true, subtraction. Because if we have 1 minus 2, and then we'll close up that, and then we'll minus 3, what we're going to get is 1 minus 2 is negative 1. Negative 1 minus 3 is negative 4. And then right here, let's say we have 1. Let's say we have 1. Sorry about this. Let's say we have 1 minus bracket. We're going to subtract 2 minus 3 first. Now 2 minus 3 right here is going to make it the negative 1. And then 1 minus negative 1 is positive 2. Positive 2. Now, negative 4, positive 2, that now work out. Them they are not the same. And so clearly it's not true for subtraction. Obviously, associative law cannot be true for division, as 1 divided by 2 divided by 3. And let's say we divide 1 divided by 2 first. 1 divided by 2 is a half. And then a half divided by 3 is going to be equal to 1 over 6. So we get 1 over 6. Now let's say we were dividing now first. 1 divided by 2 divided by 3. And let's say we start with 2 divided by 3. So this would becomes 1 divided by 2 over 3. And 1 divided by 2 over 3 is clearly going to be 1 times 3 over 2, and 1 times 3 over 2 is 3 over 2. So clearly these two results are not the same, and so what can we conclude? We can therefore conclude that the associative law only holds true for addition and multiplication. So the commutative law under the real number system only holds true for addition and multiplication. And the commutative and the associative law only holds true for addition and multiplication. So division and subtraction does not hold true for either commutativity or associativity. Now the next law that we learned about from primary school is distributive law. Alright, and in primary school, how we would learn it is I remember what my teacher told me in primary school. She said any constant k times the sum of a plus b, the k distributes inside of the bracket to get the sum of ka plus the sum of kb. I've always remembered that from primary school. From primary school, my teacher said the k, it's going to distribute. All right, so the k1 add to both of them, so it becomes k times a plus k times b. So the k distributes inside the bracket, and k1 times both of them, and then take the sum. All right, the k1 to be a part of both of them. So that's why I put the bracket. That's what she told me, and I've never forgotten it. Now the distributive law, it works. It works for, of course, again, addition and multiplication. That's when the distributive property works. All right, so here's an example. Let's say we're multiplying a times b plus c. The distributive law gives us that if you remove the times right here, it's really a bracket b plus c. You're going to get a times b plus a times c. All right, that's the distributive property. And so in that case, we say that multiplication distributes over addition. Multiplication distributes over addition. All right, multiplication distributes over addition. Multiplication also distributes over subtraction. So we have a times b minus c is equal to a times b minus a times c. Let's look at some examples to show why that is. So showing the distributive property, k times a plus or minus b, and show that it's going to work out to be equal to k times a plus or minus k times b. That's the distributive property that we're showing. Now look at this now. Let's say for example, we have 5 times 3 plus 2. 5 times 3 plus 2, as we know it, that should be equal to 5 times 5, and 5 times 5 is 25. So now let's check if multiplication distributes over addition. Multiplication distributes over addition if this is going to be equal to 5 times 3 plus 5 times 2. So distribute multiplication over addition. 5 times 2. And so what we get, 5 times 3 is 15, plus 5 times 2 is 10. And so it works out to still be 25. And so what we say is that multiplication distributes over addition. All right, and so this is true because these two are the same. Now let's say it was minus in here. So let's say we have 5 times, let's say 7 minus 2. And this is the 7 minus 2 to get back to 25. Because 7 minus 5 is 5. 5 times 5 is 25. Now let's see if it distributes over subtraction. So we get 5 times 7 minus 5 times 2. And so what we would get then is 5 times 7 is 35, and 35 minus 10 is 25. And so what we can clearly see from right here is that multiplication distributes over subtraction. Easy, soft. Now since multiplication distributes over subtraction, what we can therefore conclude is that multiplication distributes over addition and multiplication distributes over subtraction. However, multiplication does not distribute over division. Multiplication does not distribute over division, and division does not distribute over multiplication. So these are the only two cases where we can use the distributive property for the real number system. Remember, everything is for the real number system. All right. The next thing to look at on that real number system is inverse and identity. So what is identity, you might ask? So what is, for example, I am known as Ronaldo. I am Ronaldo. What is my identity? Identity under addition means which number, when I add to Ronaldo, I'm still going to get back Ronaldo, or what does not affect Ronaldo. Which number does not affect Ronaldo is the identity of Ronaldo. I don't know if that makes sense, but yes. So that's what pretty much identity is. When you do an operation to something, but it still remains the same, that's its identity element. And so the identity element of addition is, let's say we have some number A. Which number, when we add to A, we're still going to get back A? That number is 0. And so for addition of numbers under the real number system, the identity is 0. So addition identity is 0. For multiplication, the identity of multiplication is 1. Which number, when you multiply it by that number, you get back the original number. So if the original number is x, x times what give you x? That's 1. X times 1 equal x. And so we say that 1 is the multiplicative identity. All right. Now the next thing we have to look at is the inverse for addition and multiplication of real numbers. So the inverse is which number that when I carry out this operation, I get back the identity. So that's the inverse. So for example, I am Ronaldo. Which number is the inverse that when I add it to the original me, I get the identity of me? So that's what inverse do. So for example, the addition identity is 0. So let's say we have some number A. Which number, when we add to A, we're going to get back the identity 0. That's minus A. And so minus A is the additive inverse, all right, of A. So if you have a number x, then the additive inverse is minus x. Now, for multiplication, which number that when we multiply it, we multiply some number A by a number, it's supposed to get 1. The only number that we can multiply by A to get 1 is 1 over A. And so 1 over A is the multiplicative inverse, all right, of any number. So whether the number is B, then the multiplicative identity will be 1 over B. All right, and so that deals with identity and inverse. The next thing I want to talk about is closure. What is closure? Now a set is said to be closed. Now listen carefully. A set is said to be closed whenever we carry out a operation on a number system and the result is also within that number system. So for example, 3 minus 7 is negative 4, and 3 and 7 are real numbers, and negative 4 is a whole number, and so the operation is closed. All right, the operation is closed because 3 and 4, even though it's a real number, it's also a whole number, and so it's closed under whole numbers. So this right here, this R right here should be W. This R should be W. 3 and 7 are whole numbers, and 3 and 7 are whole numbers, but 4 is also a whole number, and so it would be, so this one, but negative 4, sorry, negative 4 is not a whole number. My apologies. Negative 4 is not a whole number. Negative 4 is not a whole number. It says set W is not closed. Set W, which means the set of whole numbers, is not closed under subtraction and division. W is not a whole, negative 4 is not a whole number, right? Negative 4 is an integer, it's a negative integer. And so this is not closed under whole numbers. Now this would actually be closed under real numbers because 3 and negative 7 are real numbers, and the result negative 4 is a real number, and so the set would be closed under the real number system. But it would not be closed under whole numbers because 3 is a whole number, right? 7 is a whole number, but 3 minus 7, the result, is not a whole number, and so it cannot be closed under whole numbers. Don't worry, we're going to do a lot of examples that we're going to see how these things work. All right, and the second example is the same. We're adding two whole numbers. So 9 and 2 are elements of whole numbers, right? but negative 4.5, that's a fraction, and a fraction is a rational number. Rational number is not a whole number, and so clearly it's not closed under whole numbers. Finally, the next thing to talk about on the real number system is the Cartesian product. And what is Cartesian product? If we have two non-empty sets, A and B, right, we can write them as a set of ordered pairs, and we write the ordered pairs as A cross B. All right, and so if A and B, right, A is an element of A and B is an element of big B. So let's say, example, look at this example right here. So A is equal to 1, 2, and B is equal to A, B, C. So A cross B can be many things. A cross B can be 1 and A, or it can be 1 and B, or it can be 1 and C. It can be 2 and A, 2 and B, 2 and C. That would be A cross B. Now what if we want B cross A? B cross A would mean we have A1, A2, B1, or B2, or C1, then C2. Now what is A cross A? A cross A would be 1, 1, 1, 2, 2, 1, or 2, 2. What would be B cross B? B cross B would be AA, AB, AC, or it can be BA, BB, BC, or it can be CA, CB, CC. That would be B cross B. That's known as Cartesian product. We're going to look more into Cartesian product when we're doing coordinate geometry, Cartesian equations, and stuff like that in module 2. Alright? Easy stuff. Alright. And that pretty much takes care of what we need to know about the basics of the real number system. Now we're going to finally get into binary operations.